All right, so in this particular video, we have two blocks, a stack on top of one another, and it says that it can move without friction on a horizontal surface as shown below, and then the surface between the two blocks is rough, and that the coefficient of static friction, mu s here, is equal to 0.45, okay? So here is the diagram. Here are two blocks. M1 is 5 kilograms that sits on top of a friction surface, and then M2 rests on top of the 2 kilogram, on top of the 5 kilogram block on the bottom. All right, the force is being applied to the bottom block, and then the problem states that the coefficient of static friction between the two blocks is 0.45. Part A, it says if a horizontal force F, which is this F here applied to the bottom block, is applied to the 5 kilogram bottom block, what is the maximum value F that can have before the 2 kilogram block starts to side off, okay, or steps off. Part B asks if the mass of the top block is increased, does the maximum value of F increase, decrease, or stay the same? All right, so let's crack this out. So let's knock out part A. Part A, it said if a horizontal force F is applied to the bottom block, again, these problems varies whether you're pushing the bottom or top block, but in this case it's pushing the bottom block. So it says what is the maximum value F can have before the 2 kilogram block starts to slip off. Well, as stated earlier, this particular problem suggests that M2 and M1 are currently moving together. It wants this critical value where M2 will actually starts to fall behind. So in order to do so, you should find the maximum acceleration that M2 can have based on the coefficient of static friction given. So here, the dashed line that just came up on the screen, in case you didn't notice that, that is the surface between M2 and M1. Okay, so you should recognize that along this M1 and M2 that there is a force of static friction. Just like your contact forces, there are two arrows pointing opposite of each other based on the perspective of M2 or M1. Placing a box on top of M1 causes the system to slow down. So if you're looking at M1's perspective, you would use the arrow pointing left because you need an arrow that slows the system down. However, you're pushing the system to the right. So if you're asked, well, what is causing this M2 to move? And when it does move to the right. Therefore, you would have to use this arrow that's pointing to the right. So while you have two vectors that are opposite and equal in magnitude, really it's the same vector. It just serves a different purpose based on your perspective. Okay, so once again, if you look at M2, what is causing this M2 to move to the right? It's this F of S that's pointing rightward. However, if your perspective is on M1, well, what's slowing down M1? Placing a box on top of M1 can only add more mass to the system, which would suggest that it is going to slow down. So therefore, if you're looking at M1's perspective, you'd have to use Fs pointing leftward. All right. So let's go ahead and set up the physics for M2. In order to figure out what the maximum force you can apply to the bottom block, well, you have to figure out how much acceleration the top block can handle, right? So I'm going to use Newton's second law of motion here, sigma F equals ma, but you notice here I am focusing on block 2. I need to figure out how much acceleration M2 can handle because I'm pushing the bottom block and M2 is just going to move as a result of this static frictional force. So therefore, the net force acting on M2 is simply this F of static pointing to the right. So if I'm looking at M2, there's only one force that I can use. It's this F of static, okay? F of static is going to equal to M2 AX. It's M2 because I'm using M2's perspective right now to find F of static because it is the easier one to do. Well, by definition, F of static is simply mu S times F of N, which is equal to M2A. But this F of N here is tricky, right? You got to focus on the mass that you're looking at. Right now, I'm setting up the physics for M2, which is the top block. Well, here's where my surface is. So I'm looking at M2, here's my surface. So I can totally visually ignore M1 for now because the surface that M2 is sitting on is the top of M1, which I can just treat it as like a floor. So therefore, I can set up the weight of M2. So therefore, if M2 is resting on the surface, aka imaginary surface here, M2, it has a weight, which is F of G2. and that F of G2 is just simply mass 2 times gravity. But there is a counterforce, a contact force that pushes up on M2 from M1's surface that I just treat as the floor for now. So therefore, the arrow pointing up is your normal force due to block 1 onto block 2. Okay. We know that these two values are equal in magnitude, so therefore I can say F of n is equal to the magnitude of F of G2. So therefore in my work, I simply replace F of n with F of G2, but F of G2 is just mass 2 times gravity. So hopefully by now you can see that M2 cancels out. It appears on both sides of the function. We can cross that out. So therefore to find the acceleration of the top block, we simply take the coefficient of static friction times it by gravity. And if we plug in values, the coefficient of static friction is 0.45, the acceleration due to gravity is 9.8, and if we simplify that on our calculator, we should get a value of about 4.41 meters per second squared. Okay, but as you practice the stack box systems, you have to interpret information correctly. What did I just find? I just found the acceleration of the top block. Okay, so to me, this 4.41 meters per second squared is the maximum acceleration that the top block, aka M2, can withstand before it starts to fall behind. Because if you push harder on the top block, if you push harder on the bottom block will accelerate faster, which causes M2 to fall behind. But for now, this is what it's interpreted. So AX is 4.41. So this is the maximum acceleration that M2, the top block, can handle before it starts to fall behind. Okay. So now that we know the acceleration, we can find the net or the applied force here on the bottom block. Okay. So according to this diagram, you're pushing the bottom block, but really you're pushing the whole entire system because it's assumed that the M2 is going to go with M1 because it uses the phrase static coefficient. Okay, so you're pushing M1, but M2 sits on top of M1, so really you're pushing two masses. So I'm going to use Newton's second law again, except this time though, I'm going to set up for the whole entire system. Well, F here is pushing both M1 and M2 as a result. So for net force here in the system, I'm simply going to replace sigma F system, which is F, because that is the only force that is present. And the frictionless surface here has nothing to do with the problem, okay? So the fact that it says frictionless on the bottom here makes the problem easier, all right? So there's nothing to subtract it from. So it's just F, and then what is M? It would be M total. So why F is only pushing the bottom block, putting a top box on top of it would cause it to be quote-unquote heavier. So really you're pushing both masses. All right, so if that's the case, I'm just going to expand M total into M1 plus M2 times AX. Well, we know what the total mass is. The total mass is simply 5 plus 2. So 5 kilograms plus 2 kilograms, which is 7. The acceleration that we just found is 4.41. Therefore, F here is just 30.87 newtons. Okay, so this is the maximum force that you can apply that will generate the same acceleration for the system before M2 falls off, which makes sense. Because if this F is greater than, let's say, 31, what if its F is 32 and 40 and 50? Pushing the bottom block would cause the bottom block to accelerate faster, but there's not enough friction here to hold the top block relative to the bottom block, so therefore it will eventually fall off. Okay, so as you find these values, make sure these answers make sense. All right, part B says, if the mass of the top block is increased, does the maximum value F increase, decrease, or stay the same? Well, I highlight this function here. F is equal to M1 plus M2 times AX. Okay, so my answer is going to be that based on this function here, if M2 is increased, right, this parentheses goes up. If this parentheses goes up, and assuming A doesn't change, then F has to go up. And so therefore, the statement here is F increases due to the function F equals M total times AX. So if the total mass of the system goes up, well, you're pushing more mass, but therefore if you're pushing more mass and if you want the same acceleration, you would have to push with more force, which makes sense. Okay, all right, I hope that helps. Stay nerdy, don't be whack.